Here to introduce tonight's speaker from the Boeing Company, hopefully he does better than I did, Steve Shestak.
Please join me in welcoming to the Distinctive Voices podium, Dr. Thomas Harter.
Thank you, Steve, and thank you to the National Academy of Sciences for having me here tonight. And the timing could hardly be any better. If you've seen the newspapers today, I couldn't believe it seeing the article in the LA Times on subsidence in the Central Valley, and U.S. News and Report had an article on today. So water is certainly on everybody's mind, and I will focus on the groundwater part of that water equation tonight and how that relates to what's on everyone's mind today in California, which is the drought. And we've seen all these pictures of the empty reservoirs, of reservoirs with long bathtub rims and no snowpack to fill them this year. And certainly being either here in Southern California or anywhere in Central California this winter and not really having seen a lot of rain for the fourth year in a row seems spooky to many of us. Orchards are going dry, fields are being fallow, people run out of water, especially in our rural communities with small community water supply systems. Their straw no longer is deep enough in the groundwater systems, and they are forced to haul water in from distant places and paying a significant amount of their income for just drinking water. And the drought has no end in sight. It's not just captivating California, but much of the West. And it's now in its fifth year almost here in California. Now, while the last 2 or 3 years, none of them in particular has been anywhere as low as our record 1920s, late 1920s drought or our 1977 drought. When we look at the running total for 3 years, the last 3 years have indeed actually broken records in the measured history of California, and we're at the lowest level we've ever been in the cumulative rainfall record for 3 years here in California. And it's that 3-year record that you will learn tonight is really important to our groundwater resources and not just a year-to-year variability. This year looks like no exception. We are currently scooching along the bottom of cumulative precipitation in Central and Southern California, and looking at my weather forecast, it's not looking that great for the next 10 days, and then winter is pretty much over. So what I would like to do tonight is cast that in a larger picture of how groundwater works, what happens to groundwater in drought, and what happens to groundwater when it's overdrafted. Talk about how can we change that, and how do we do sustainable groundwater management. And what about groundwater quality? Groundwater management is both management of supplies and management of water quality. And we'll kind of cast it in a large arc. And I want to conclude by kind of pointing it back to you and your decisions and how you can get involved on this matter. So how does this all work? We all know that California is kind of a dry state. We have wet winters, dry summers. We have a wet north, a relatively dry south. We have this disconnect in space and in time between where rainfall happens and where water is used. Rainfall happens in the winter, we use it in the summer. Rainfall happens in the mountains, we use it in the valley. It falls in the north, we need it in the center and in the south. Well, California has come to use it, and we've built a huge infrastructure around this. The water users are agriculture. We have about 10 million acres of irrigated agriculture, mostly in the Central Valley, in the Imperial and Coachella Valley, and along our coastal basins with a few of the inland basins. But most of the water use is really here in the Central Valley and our southern coastal basins for agriculture. In total, agriculture uses anywhere between 27 and 35 million acre feet per year. The urban users also sit in the central and southern part of California. As you all know, Urban users are on the order of about 8 million acre-feet per year. They're about a quarter of what agriculture uses. And then there's the environment. We have about 45 million acre-feet allocated for wetlands and dedicated stream flows in California. And that gives you an idea of where these water uses are in California. Now, to get there, we've built a large network of canals. We've built reservoirs and dams. The reservoirs and dams, they are at the foothills of our mountain ranges, not just the Central Valley, but also mountain ranges down here, mountain ranges along the coast, where we keep that spring runoff from our mountains to hold it over for the summer, and maybe for the summer after that, if it's a dry year. And we've built a large network of canals that's connecting our northernmost mountains all the way down to San Diego, and we can actually redistribute water throughout the state to fix that disconnect between where water occurs and where water is being used. And at the very center of this infrastructure sits the Sacramento-San Joaquin Delta, and most often when we talk about water, that's where we usually go and talk about all the environmental issues here in the Delta and why all the rest of the state is hooked to this Delta, which is really the Grand Central Station of water in California. But I want to deviate here from that story and actually focus on something else, and that's the hidden resource of water that we have in California, and that's our groundwater. What is groundwater? People talk about arteries. People go around with pendulums, and dowsers go around with sticks to try to find these arteries that are hidden in the subsurface. But what groundwater really is just what you have at home in your flower pot, just a little bit more of it. Think of that flower pot at home. Take an empty one, put your thumb at the bottom hole, pour some dirt into it. You haven't put any arteries in there. You haven't put any underground reservoirs in there. You haven't put any box of water in there, right? Just stuff it with dirt. Take your watering can and fill water in it. The water disappears. Where does it disappear into? Not into arteries, not into a cavern in that flower pot. It just disappears into the pore space between all the dirt particles that are in your flowering pot. And California groundwater basins are much like your flowering pot, a little bit larger. They look a little bit more like a bathtub that's filled with sediments. So instead of the flower pot, you have this bathtub. And what you see here in color are the bathtub walls, the ancient rocks of California. And what you see here is that sediment fill that's in that bathtub. And it's in that sediment fill where we find most of our groundwater. Granted, there's quite a bit of groundwater in the fractures of these rocks as well. And any of you who owns a home in any of the foothills with a domestic well knows that it's enough to kind of get water for a house. But to get water for a big city or water for agriculture, we need these large sand and gravel aquifers that fill these bathtubs all around California. These are our large groundwater basins with hundreds of millions of acre-feet of water, much more than we have in any reservoir here in California. Here's a cross-section and a quick way to illustrate this. Your flower pot, the potting soil in it, or your bathtub and the sediments in that bathtub. And over time, as rivers have come out of the mountains and scooch over these sediments, they lose water into these sediments and fill up the groundwater. Rainfall goes onto the soil, and to the degree it's not used by plants, it percolates down into this bathtub, into these sediments, and fills these sediments up with groundwater. And so this groundwater eventually comes out. Where does it come out? Well, you've all seen it. If you have a little hole in your flower pot or on the beach, you can see that groundwater coming up in that soil, and the same happens here. And that lowest point in the sediment surface in our valleys, that's usually where our rivers are, right? And when we fill up this groundwater basin some more, then we create a slope in this water table surface, which lets the water move from the higher places of water table to the lower places of the water table. And groundwater moves essentially to these rivers. So the balance is going to eventually be the recharge coming in from rivers and from rainfall, and then groundwater discharging to the river at the bottom of the valley, the large river that ultimately drains all of this into the ocean. Now, in the early 20th century, we started drilling wells. We invented the turbine pump, and we were able to actually extract large amounts of water from these aquifers that we have in these large sedimentary basins of California. And so mostly in the summer, we create these large cones of depression around these wells. We turn them off in the fall, and as a result, with recharge coming in from streams and rainfall, the water table recovers, and we go with this back and forth. And so in this way, groundwater really becomes a storage reservoir, and it becomes part of the solution to carrying over water that's available in the winter for use in the summer. It's another reservoir. And we can see that when we look, for example, at the landscape water budget in the Tulare Lake Basin, where we have, and this is showing month-to-month water budgets for the landscape in a normal water year, where above the zero line, you have all the water inputs to the landscape, and below the zero line, you have everything that gets lost from that landscape. The light blue color is the rain. The intermediate blue color is river water that's being applied as irrigation. In the dark blue, that's groundwater extraction for irrigation. The red is what the plants use, and the orange and yellow is what percolates down to groundwater from streams and rivers and from the landscape in terms of what's left over after irrigation and not used by plants. We have rain in the winter. We irrigate with groundwater and stream water in the summer. That rain in the winter leads to a lot of recharge, both from streams but also from the landscape. And the same with irrigation in the summer. It actually creates a significant amount of recharge to our groundwater aquifers. That's part of that groundwater balance. Now, in a wet year, there's even more recharge happening because we have more rain, less irrigation, especially in the early summer. We almost see no irrigation. And most of the irrigation happens in the later summer. So there is a surplus of water that's ultimately not actually being used in this particular year. And then we have dry years. In dry years, we have little rain, and all the irrigation, which happens for an extended irrigation season now, comes from our groundwater basin with very little recharge to balance that extraction. And so not only do we save water that's being recharged in the winter for summer use, but we also take that water that's being recharged in wet years and use it in dry years. So these groundwater basins are actually large enough storage reservoirs for long-term storage and use. And so in some years, we see, and again, here's the supply on the right side and the demand on the left side. We see that in some really dry years, like 1977 drought, in this particular part of the southern Central Valley, more than half of the water use comes from groundwater, whereas in really wet years, like the mid-1990s, it might be as little as 20 or 25%. On a statewide basis, the same thing. In wet years, we use maybe 12 million acre-feet of groundwater, maybe 15 million acre-feet of groundwater. Last year, I'm estimating that we probably used well over 20 million acre-feet, if not 24 million acre-feet of groundwater. And that's how our groundwater basins are used as storage basins. But not only that, we also use our groundwater basins as a canal, so to speak, and only figuratively speaking. We use it as a conveyance facility. If you look at this particular part here in Tulare County, we have a whole bunch of different water districts. They all have different water rights for surface water. Some have a lot of surface water available. They irrigate a lot, and they lose a lot of that irrigation to groundwater, which tends to be beneficial from a water supply side, even though there are sometimes water quality issues related to nitrate, as we will see later. But these water districts have a lot of water supplies. They tend to have quite a bit of recharge to groundwater, whereas this district here in the middle, which has very little access to surface water, instead pumps a lot of its irrigation water from the subsurface. As a result, groundwater that piles up under these districts flows into this district. And so district actually gets about 70,000 acre-feet of water every year through underground flow from these groundwater basins or across this groundwater basin and essentially delivered. And if we look at the Central Valley as a whole, colleagues of mine have done modeling exercises, and between these larger groundwater basins, we see groundwater exchanges that are on the order of tens to hundreds of thousands of acre feet each year. So there's a lot of groundwater transport as well happening. So we go back and forth in this system, and where it gets a little bit more critical is when the balance between what we recharge into this groundwater basin and what we take out of this groundwater basin is out of whack. When we take more out than we recharge, especially during extended droughts. Well, here's an example of what happens in drought periods in wells in the Central Valley. This is in Tulare County. This is a record from 1950 to 2010. You can see the 1977 drought right here. We see about 10 foot of drawdown on this water level in this particular well in 1977. We have another drought in the late 1980s, early 1990s, going on for over 5 years, losing 10 feet of water level each year. In the drought in the early 2000s, we even lost 15 feet on this particular well. And so it's no surprise that this well probably has similar amounts of water level changes now in this most recent drought. Other wells have more drawdown depending on pumping behavior, depending on construction, depending on how the aquifer exactly looks like where the wells are. This particular well during these droughts typically shows water level drops of about 40 feet from year to year, with big drops happening typically in the summer and then some recovery in the winter. What happens during a drought is that you pump it down in the summer, but then the recovery in the winter, which is kind of nice when we have an average year or is higher than the drawdown in the summer in wet years, that recovery doesn't happen in these dry winters. And so we go down through the summer, we don't recover in the winter, and we go down again in the next summer. That's what we see during drought. I thought I'll look at a well near here in the Beckman Center. We're sitting right here. If you look across the water on the other side, north of here is a well that I'm going to call the Duck Pond well. And then a couple miles to the north of here, also along the San Diego Creek, is another well for which I have data, which I call the San Diego Creek well. Well, the green one is the Duck Pond well. That's nicely going down in the summer, up in the winter, down in the summer, up in the winter. And during the early 2000s drought, we lost about 2 feet per year from winter to winter to winter to winter. In the more recent drought from 2007 to 2009, we actually lost about 6 feet per year going from winter to winter, but it recovered very nicely in 05, 06. But we then don't have any records going past 2010. The well out here varies a little bit more. It's going summer to winter. It's a pumping well, so the variations are larger. We actually lost about 7 feet per year in this drought and 10 feet per year in the 07-10 drought. Now, if I look at the most recent drought, it then comes as no surprise, as I said earlier, that we're losing about 10 feet of water per year in this particular well, and this year will not be any different from past years. So there is some predictability in this system. If we look at the long record for these for this particular well here, this well has actually records going back to the 1930s. We've seen this same behavior in the drought in 1977. We've seen it even in the droughts in the early 1960s, and around 1950 we had a drought. And there were significant drawdowns between the 1930s and the 1950s when massive groundwater development first began in this region, and before we had State Water Project water and Central Valley Project water down here in the south. This picture of drawdown on the order of 10, 20 feet per year is repeated all over the state. This is the total drawdown in water levels between 2009 and 2014, spring to spring, and you can see many wells that have more than 10 feet of drawdown, except some of the wells that are right here along the coast in the Southern California, and I'll explain that here in a minute. When we look and compare the lowest water levels that we've measured in the 20th century, which typically has been in the mid-1950s in a lot of southern and central California, and we compare current water levels with where we were in the 1950s, we're well below where we were at the record lows in the 20th century, especially here in the southern part of the Central Valley, not as much here in Southern California. And that explains why people are now estimating that on the order of 130 million acre-feet of groundwater in total has been lost. This is about 3 to 4 times as much as we have surface water reservoirs in California. We've lost out of the Central Valley, mostly the southern part of the Central Valley, over the last 100 years. Now, there's still a lot of groundwater left, but there are many consequences to this kind of groundwater depletion long before groundwater is actually gone. Let me talk about some of these consequences. Seawater intrusion is the one that you're most concerned about here in the south. Normally, we have groundwater that's pressurized with a water table that's typically near the land surface. When that happens, groundwater flows usually in the direction of where this water table surface is sloping. So it's typically sloping under natural conditions from the land where we have recharge to the ocean, and that makes groundwater, fresh groundwater, flow out toward the ocean. There's a little bit of seawater right here on the beach. But when we put pumps in on the inland side, that water level surface actually declines, as you've just seen in the graphs I showed for the wells here. And that means that now the direction of flow is in the other direction, and that pulls in the salt water. And in places where in the place here, you can see we have sea level here. This well out here has been below sea level in the 1950s and 60s, nicely recovered in the 70s and 80s, and has since seen some downturns, partly because we've had so many dry years in the last 15 years, more so than in the second part of the 20th century. Even this well that's out here, not that far from the beach, is now below sea level. In some places where this has gone unchecked for decades and where local water agencies haven't really done anything about, like in the Salinas Valley, that has led to seawater intrusion that goes now 8 miles inland. This is Salinas. The city of Salinas is right here. The city of Monterey is just to the bottom left here off of this slide. Huge amounts of seawater intrusion here in the Salinas Valley. Another consequence of this tremendous drawdown in groundwater levels is the cost of pumping. As we draw water levels down, each year the cost of pumping goes up. Some of the wells fall dry because they're not deep enough. And that's really then the big cost. Drilling a new well and spending $50,000, $100,000 for a small domestic well, $1 million or $2 million for a large urban well or for an irrigation well that has to be drilled to 1,000 feet or 1,500 feet. That's no small feat. We're estimating, colleagues of mine have estimated that last year the cost to agriculture has been, the drought impact to agriculture has been on the order of $2.2 billion. About 20% of that is due to the cost for drilling new wells and pumping and lifting that water an extra 20, 40, or 100 feet. Land subsidence. That was the headline today in the LA Times. Another big consequence of groundwater pumping. Why do we have land subsidence as part of groundwater pumping? That's because all these bathtubs that are filled with sediments, part of the sediments is not just sand and gravel, but a big part of it is clays. And clays typically, when they're in these sediments, when they get deposited, clays get deposited in the bottom of lakes or in big floods. They get deposited wet, and the clay particles actually stay wet and keep their wetness. They become basically embodied into groundwater right away. And as a result, the clay particles, which I'm representing here with my fingers, they don't quite touch each other, or just a little bit. And as they get buried under ever more deposits, there's two forces that act on these. On one hand, they want to squish together because they're holding this huge sediment pack on top. On the other hand, there's water between them, which is pressurized. There might be 100 or 200 feet of water above them, and if you've ever tried to hold a 100-foot column of water and not been able to do so, you know how much pressure that is. So that water pressure actually keeps these clay particles apart. But as we lower the water table, we decrease the pressure without decreasing the sediment overload. And that squishes these clay particles together. And they cannot be pushed back apart. Once they get pushed together, they cannot be pushed back apart. And as we have enough clay in some of these areas, all these areas that are shown here in red have significant amounts of clay as part of these sediment packages that are sitting in these bathtubs. We can see significant amounts of subsidence if water levels drop below levels that we have seen historically, which is the case particularly, as you saw earlier, in the southern part of the Central Valley. And indeed, last year alone, we have seen large areas. This is the city of Fresno. This is the city of Merced. Here is Visalia. So we're looking at almost 100 miles from across the southern part of the Central Valley, across the whole width of the Central Valley. And there are many areas in yellow and red that have seen more than 6 inches of land subsidence over the entire landscape. These areas in the 20th century have already seen some areas as much as 30 feet of land subsidence, and in some areas we're starting to go for that record again, with huge consequences to slopes in canals, bridges that go over canals, and the water infrastructure in this region. I've called last night a couple of my colleagues here in Southern California to find out whether there's any subsidence issues here in the LA Basin or in Orange County, and I was affirmed that there is, because what we will see, because groundwater levels haven't gone down the way they have in the Central Valley, there's no such land subsidence issues down here in Southern California. Other impacts of droughts that are related to groundwater is we lose some of our springs, and the vegetation that's associated with springs is really struggling in these droughts. And we have a lot of these groundwater-dependent ecosystems that depend on springs all around California, mostly in the mountain ranges. Our wetlands around the Delta and in the Sacramento Valley and out in the desert are suffering from this drought as well. We have lots of areas with wetlands that are groundwater dependent. And more importantly even, the rivers. These rivers now, instead of receiving water that used to come to them, they're now losing water that's going to these wells that we're pumping for irrigation and for urban water uses. And many of these rivers in Central and Southern California, as a result, have gone dry. This is a map that was recently published showing where the rivers are most dependent on groundwater to supply that base flow that we have during the months when it's not raining. So how do we deal with all of these conflicts? There's a lot of trouble here. How has California dealt with this? Drought is not new to California. The current drought may be the largest we have seen in the last 120 years. Combined with some of the climate change effects, it may have bigger impacts on California than any of the droughts before. But droughts have been part of the California landscape since the state was founded. And as a result, we've actually had established groundwater rights. We have a correlative rights doctrine, which under our court system clearly states a clear philosophy of how we divide up groundwater in the state of California. What the correlative rights doctrine says is that the right to pump groundwater, and only that part to groundwater that can actually be replenished on a year-to-year basis, the right to pump groundwater that can be replenished is correlative to landowners' size, the size of landowners' parcels, and to the properties of the aquifer. So, in other words, all the landowners across the groundwater basin share that resource, the replenishable part of that resource, in correlation to the size of their properties, their land property. They don't share, and nobody has a right to empty out our aquifers. This is going back to court decisions that have been handed down in 1908 and have been since confirmed in many court decisions. We have a constitutional mandate for beneficial uses. We can't just waste water. We have many special districts, and Southern California is full of special districts that deal with water and water issues, including the Water Replenishment District and Orange County Water District, that deal with groundwater and groundwater management. Counties, under their police power, can terminate exports of groundwater and can manage the transfer of water. Just today, San Luis Obispo County moved forward on considering a prohibition of groundwater exports out of their county, and Merced County issued a groundwater ordinance yesterday. Then we've always had the courts. When people fight about groundwater and they can't agree on something between them, they can go to court, and the courts use the correlative rights doctrine to divide up groundwater. In Southern California, we've seen many court cases that have led to what is called basin adjudication. A basin adjudication is a process whereby essentially all landowners send their attorneys to court, they divide up water in the court, and decide who gets how much water. We've seen many of these adjudications here in Southern California. And then, as groundwater, especially in Central California, has been depleted over the last 30 years, a little bit more with each drought has yielded a little bit more of legislative action. So the late 1980s, early 1990s drought yielded AB 3030, which for the first time suggested that locals do groundwater management plans and provided a framework for these groundwater management plans. In the early 2000s, with the next drought, the state went one step further and said, if you want money from us for your water projects, you better have a groundwater management plan. And so that was SB 1938. And with the current drought, which from a groundwater perspective really has been going on since 2007 with 1 year interruption in 2011, we have finally managed last year to pass a sustainable groundwater management bill. That sustainable groundwater management bill takes what courts have long decided and makes it policy of the state that groundwater be managed sustainably for long-term reliability and multiple economic, social, and environmental benefits. And the statute lays out how that is being done. The first step being that groundwater sustainability agencies be formed in all of the so-called high and medium priority basins, everything that's orange and yellow. Within the next 2 years, all these areas have to have groundwater sustainability agencies that then implement groundwater sustainability plans. Now, many of these agencies, and it still is to be determined who those will be, many of these sustainability agencies have groundwater management plans that have been developed in the past to rely on, to at least for a start. They will have to develop these groundwater sustainability plans within 5 years. And what these groundwater sustainability plans are essentially 4 things. For one, they are a communication between many different stakeholders that are all sitting in the basin that all have a stake in how groundwater is being used. They contain descriptions of the groundwater basin. They have monitoring activities. They include processes for accountability and review. A lot of this has been part of groundwater management plans in the past. What the new law does is it empowers these agencies to actually do enforcement. They can prohibit pumping. They can make charges for groundwater pumping, and this has been the case for some special districts in California, but not as a rule for all of California. This makes it possible for all these groundwater sustainability agencies to engage in these much more rigorous management activities. It suggests integration with surface water management, integration with water quality management, and it also for the first time makes a linkage between groundwater management and land use, which of course drives all of the groundwater pumping. So in essence, it's a data collection, monitoring, and assessment process. It's management of the demand side, of the supply sides. It's managing the recharge, and it's managing the demands. You want to manage that bank account. You want to increase how much goes into that bank account, and if there is not a balance, you want to decrease how much comes out of that bank account. And a lot of that requires engaging your stakeholders and managing your stakeholders. Those are the 4 key tasks of these groundwater sustainability agencies. And nobody has more experience with these processes than Southern California. Southern California has many urban water districts that for the last 50 to 80 years have engaged in these processes because Southern California was the first place where groundwater basins started to empty out when large-scale groundwater pumping happened. And where many of these impacts that I just described started to occur as early as the mid-20th century. One being pumping, leading to seawater intrusion. So what these agencies have done, like the Water Replenishment District and Orange County Water District, they have built seawater barriers where they inject groundwater to build up this water table that prohibits seawater from intruding into the groundwater basin. This is a slide from Orange County Water District. They have multiple aquifers that are impacted by seawater intrusion, and through their injection wells, which initially, the initial projects were constructed in the 1950s and 60s, they have managed to keep seawater intrusion at bay, unlike what the Salinas Valley has seen, which I showed earlier. The Central Basin, Los Angeles County, they've seen dramatic drawdowns in the 1940s and 50s, and through a combination of providing additional groundwater near the coast, injecting groundwater near the coast, developing additional groundwater, surface water storage, local surface water storage, by bringing in water from Northern California. The LA County, just like Orange County, has managed to recover its water levels to something that's much closer to sea level. We have built groundwater banks both in the southern part of the Central Valley. Kern County Water Bank now stores 2.5 million acre-feet of water for long-term storage. Southern California has about 400,000 acre-feet of water stored in its groundwater basins for taking out during dry times. A lot of this water is stored by putting it into basins and letting it infiltrate from these basins, and then pumping it out during the drought. Here in Orange County, we have the Groundwater Replenishment Project, which takes wastewater, puts it through an extensive treatment process and a reverse osmosis process, and now supplies about 25% of the recharge to the groundwater basin in Orange County. So with many of these different management activities that have taken decades to develop, Orange County, as an example, has a wide variety of options to put water back into the ground. We have recharge from stormwater. We have, in brown, recharge from the Santa Ana River. We have storm flow recharge, intentional recharge of stormwater. We have imported water as part of the equation. And we have the Groundwater Replenishment Project now as part of this equation as well. And you can see we're recharging on the order of 200,000 acre-feet of water here in Orange County each year. And with 100,000 coming from the Groundwater Replenishment Project, that is actually a significant portion, on average about 30% of groundwater recharge in Orange County. And over the county as a whole, over the water district area as a whole, water levels since the 1950s have significantly recovered. Yet you do see we have a management going on here. Every drought we have seen, the 1977 drought, the 1990 drought, the 2000 drought, and then the 2007 drought, and the most recent drought, we draw down on this bank account, on this large storage reservoir, and we hope to recover in wet years. And what's happening here is we're probably by now somewhere in this region of groundwater storage. Once this line falls below this blue area, that's when additional measures need to be taken. And when we talk about getting close to where we're outside of this target zone, if we have another year like this year in the coming winter, then we're going to get close to this line, at which point Orange County probably will take additional measures to save up on its groundwater. And that will be the case in many regions in California if that were the case. And some regions will have to start to do that this year, partly depending on how much they need groundwater, shown here in purple. In Southern California, you use more than 1/3 of your water comes from groundwater. You've also developed a significant amount of recycled water and water reuse, in addition to local projects to make up for mostly urban demands of water. The Central Valley has mostly agricultural water demands. In the southern part, groundwater is a big part of it. In the northern part, much less so. And if you go to the north coast, groundwater plays a relatively small role. There, it's stream flow that's the biggest part, and that needs to be protected. So in some parts of Northern California, like the Scott Valley here in Siskiyou County, close to the Oregon border, just off to the edge of this picture, we have salmon running the stream through this valley, competing in the summer for the water in these streams with agriculture that's pumping out of this groundwater basin that also does support this stream and the stream flow here in the summer long after the snow has melted off of these mountains around it. And what we're doing here is starting to manage water that's in excess available in the winter, putting it into this sponge, putting it into this groundwater basin, which is another one of these bathtubs filled with about 100 to 200 feet of sediments. We try to fill these sediments up with as much water as we can by doing recharge projects to support that stream flow better in these summers, while also allowing groundwater to take water out, irrigated agriculture to take water out for irrigating crops. The Sustainable Groundwater Management Act that we passed last year is built for a long time frame. The agencies have to start implementing processes, and as it took Southern California decades to get where it is today, it will take many of these water districts and water agencies in the rest of California decades to get to sustainability. The Groundwater Managed Sustainability Act is not a drought management act. And so if this drought is going to continue, there's going to be other measures that we will be looking at both locally and at a statewide basis. But there's other issues. We also have groundwater quality issues. You've heard Mr. Shestak earlier talk about how Boeing has engaged now for 30 years probably in the cleanup of groundwater contamination. And we have done lots of work over the last 3 to 4 decades to deal with industrial solvents, with gasoline spills, with paint and other industrial processes that leach chemicals into our groundwater, all of which typically are point sources and create small or larger plumes on the order of tens of acres, maybe hundreds of acres in size, and contaminating drinking water wells, mostly in urban areas. But our much larger water quality problem, groundwater quality problem, are naturally occurring contaminants such as arsenic, chromium, hexavalent chromium, which naturally occurs in many, many wells in both the mountains and in the sediments of California, and things like arsenic and uranium. But we also have nitrate. And nitrate primarily comes out of our irrigated agricultural regions and affects as many as 5% of wells statewide. In some regions, it may affect as many as 40% of domestic wells. And some studies now show that that has major impact on drinking habits of people, primarily in disadvantaged communities where sugary drinks are leading to obesity. Nitrate is not only a problem in California, it's a problem throughout agricultural regions in the United States, with areas that I show here in red, all actually having nitrate in excess of drinking water limits in their production aquifer. In California, this is a map now almost 10 years old, showing the major areas with nitrate contamination, including areas in Southern California that used to have significant amount of agriculture. 2 counties in the Central Valley have more than 40% of their domestic wells contaminated with nitrate above drinking water limit. And much of that really has been the result of a historic increase in our crop production, shown here in green, that has been essentially made possible by the use of synthetic fertilizer and the growth of using synthetic fertilizer recently slowing down, and the growth in our animal herd, in our dairy herd, which is putting out huge amounts of nitrogen as part of their manure. And if we take the total nitrogen that's excreted and that's applied together, that nitrogen far exceeds what is being harvested in our fields, and the difference converts to nitrate, which then percolates into groundwater. And so we've seen significant increases in the last 30 to 40 years in nitrate, and our prediction is that that increase will lead to these large amounts of domestic well exceedances of nitrate throughout some areas in the Central Valley at rates of 30 to 40%. The only way to get the nitrate out, or the salts that sometimes come with it, is through expensive treatment. Estimates are running on the order of $50 to $100 million per year that still have to be spent on some of the systems that are not currently able to provide adequate treatment on these nitrate contaminations. Much of this action, much of both the groundwater sustainability action and that nitrate action is really pointing towards agriculture. And agriculture is kind of squarely coming into the focus here, as you may have noticed. But agriculture also has huge opportunities here. They're a big part of our groundwater supply management. And they can be a part of that groundwater supply enhancement. They have to be part of doing groundwater quality improvement and drinking water protection. But at the same time, we have to do agriculture in an economically viable way. How to do this? That's the challenge of today and the future, much like the Superfund and the Clean Water Act have been challenging companies like Boeing and other industrial companies 30 and 40 years ago in how to deal with that. That's going to be a revolution for agriculture and a change for agriculture that will not come easy. Some say, well, why do we grow so much food here in California? And I wanted to kind of put some closing perspective on this. California, here's a drought map from this week. You can see where we have the most drought, we grow some of our most favorite foods. And some of these we only grow here. 99% of US walnuts are only grown here. 99% of almonds are only grown here. Some of our vegetables are grown to large part for the entire United States in this region. And on it goes. So there's a water footprint associated with that. And I do want to point out, while these are measured here in gallons, a quarter pound of beef has a water footprint of about 375 gallons, and a quarter pound of chicken has a water footprint of about 72 gallons. There is a distinct difference in the water footprints on the foods that we eat, especially between beef and chicken and between meat and vegetables. And I'll come back to that later. If you look at the water consumption in an average American household, this red part is the part that you actually pay for on your water bill. And that's the part that your local water agency is most concerned about and that the State Water Board in their decision yesterday was most concerned about. But the largest part really is actually our diet. And a significant part is the energy and transportation, the water that goes into energy and transportation, with much of this actually being cooling water used in our nuclear power plants and our coal power plants. But the diet is a big part of our water footprint. Agriculture is not disconnected from us. And it's not only not disconnected in California from us, but it's not disconnected from what we eat around the globe. 40% of agricultural production, whether it's food, feed, fiber, or fuels, biofuels, 40% of agricultural production happens on 20% on the 20% of irrigated lands that we have around the globe in the US, in the Mediterranean, in the Middle East, in northern India, and in places of China. That's where we have irrigated agriculture that looks much like irrigated agriculture in California. That's where we grow 40% of our food. And that's why figuring out how we can manage agriculture, its water use, and its water quality impacts is important for our global food security. As a result of being able to do that food production with groundwater as an insurance, we have seen huge increases in groundwater production, not only in the US, where much of it happened in the 1940s, 50s, and 60s and has been a relatively stable since, but very much so in India, very much so in China, Bangladesh, and some places in Latin America. These huge increases in groundwater pumping have led to groundwater overdraft, not only in California, in the southern part of the Central Valley, but also on the Ogallala Aquifer in the Midwest, which reaches from Texas all the way to Nebraska. In the southern and central part of the Ogallala Aquifer, we see consistent drawdowns of the water table, and in Texas it's now foreseeable that this aquifer is going to be essentially dry before the end of the century. We see this also in northwestern India, for example, where we've seen a consistent depletion of groundwater resources. But not only groundwater resources are being depleted there, we also have large nitrogen loads in exactly these same regions. Much of this nitrogen load comes from animal agriculture. Our demand for beef, our demand for chicken, our demand for animal products. And a lot of these regions are those regions that actually have the most population. This is a map showing the world relative not to land size, but relative to population size. And if we look at where we do irrigated agriculture is an important part and an important piece for our global population. So figuring this out and doing this is very important for our long-term food security. And you can be part of this because you make decisions on what you eat, where your food comes from, and whether your food comes from a place where there's enough water to grow that food, and where there is management that protects groundwater resources as well as surface water resources from water quality degradation. So we don't have all of the answers to those questions in place today, and part of the challenge for us on the science side will be to provide you with some of this information. Part of the challenge for agriculture will be to be more transparent in how they impact the environment with their production system. But you make that happen by asking questions, much like you made it happen for Boeing by asking questions and asking for Boeing to be sustainable, more sustainable. And I think we will have to do the same and can do the same with agriculture. And agriculture is much more responsive to consumer questions than it is perhaps to regulations. With that, thank you very much.